So I'll just go ahead and get started. I've got about 15 slides, and I just wanted to talk about two things, really, just the response of seismograph stations to the Magna earthquake and the Magna sequence, and then also just share some of our initial sort of science results from what we've been doing. And I know most of you guys already know this, but this is just where seismograph stations kind of fits in the earthquake program, the state earthquake program, and we're there in that triangle. And let's see, can you guys see the arrow, the mouse?
Yes.
Okay. So we're here, and really one of our big responsibilities is to gather the data. So basically to record seismic data, detect, locate, characterize earthquakes, and then we sort of pass that off upstream to Bob Carey's group and to Steve Bowman, these sort of other parts of the triangle. And then there's all these other agencies around here too that then take information from the triangle. And I wanted to emphasize that we have a relatively big group at seismograph stations at UUSS. And this is just a list of all of our staff and sort of our permanent staff. And basically everybody on here has been working like crazy, over the last 6 weeks on this sequence. And, the slides that I'm going to show are really sort of a group result from all the people that have been working to contribute to this and to respond to the earthquake. And this is what our network looked like on the day the main shock happened. So Wednesday, March 18, and we had over 200 stations in our statewide network. And these are all data that are telemetered basically in real time to campus, to our earthquake information center. And so we were prepared for this earthquake in terms of having all the sensors and the scientific equipment set up to record it. And so this is decades of effort going back between the state and the USGS and folks at the University of Utah and others, where we've gradually built up this sort of tremendous scientific apparatus. If we zoom in, you can see that one of the strategies was to actually have more seismometers densely packed into the urban areas. And so again, this just shows you where we were, when the earthquake happened on March 18. And a lot of these dots on here, these are the seismometer locations, and these are the seismometers that don't go off scale. So these are what we call strong motion seismometers. And when you're close to a big earthquake, these are the kind of instruments you need so that the data doesn't get clipped. And as I'll show you later, they worked really well. Here's a couple of the products that our partners at the USGS make, and these two products were available very quickly, within minutes after the main shock. And the one on the left is what we call the felt report, and each little cell on there is basically so many people that did a survey on the internet and reported the shaking, where they were. And it's almost 40,000 responses, which is really big for Utah. On the right is sort of a more scientific product where it also incorporates data that were actually recorded. And if you can see it, there's sort of some faint triangles. And in both of these products, the warmer colors indicate stronger shaking. And so you can see that there's stronger shaking, closer to Magna, closer to the epicenter, which is what we expect. And I remember on the day that this earthquake happened, several of us were downtown at a citywide press conference, and the governor was there, and the governor was giving his speech, and I could just kind of lean over the podium, and I can see that part of his notes actually included one of our shake maps in his material that he was using when he was giving his comments. So we were able to distribute rapidly these important products up the chain to different decision makers. This is another figure showing the data, and again, each one of these triangles is the location of a seismometer, and the redder, the warmer the color, the stronger the shaking. And in this case, the shaking is measured in terms of acceleration, and the scale on the bottom right is a little bit off. It actually should be %G. So our strongest acceleration was this red station here, in probably in Magna, and the acceleration there was 0.54. So 54% of G was recorded. So there was, you know, quite a bit of shaking going on, and you can see warmer colors closer to the fault plane, right? You see the oranges and the reds. But one thing to point out is the shaking depends not just on the distance, but of course on the conditions, the geology. So for instance, if you stay in the sediments and you move south, you still have strong shaking down here. But if you move east and you cross over into the stiffer soil and into the hard rock, you can see that you go from the orange to the blue, and you get much lighter shaking. So what people feel is a combination of distance to the source, but also what we call the site conditions, the geology of where they are, and also if you're in a building, the response of the building as well. And this isn't all of our data, but this is most of it. There's still a few more stations, and this is probably the world's best data set of strong motion data for what we call a normal faulting earthquake. So to have this much data recorded this close to a normal faulting earthquake doesn't happen very often. And so again, this is sort of the payoff from this decades-long experiment of monitoring our region. And now we have this data that can be fed into the engineers, the building people, and so on, and can inform decisions about building codes and so forth. So we feel really good that we were able to capture these data. These are a few pictures, and if you go to the clearinghouse that's linked on the commission webpage, you can see many more pictures like this. Most of these are from Magna, and you can see the unreinforced masonry, the brick buildings that failed here. And of course, this is one of the reasons that's always a big agenda item for the commission and for this community, really, is because you can see that luckily there were no serious injuries and no deaths, but you could easily imagine residents walking down the sidewalk near one of these buildings, or where the parapet collapses, and having a very serious injury. So I'm not going to show too many of these. And so one of the first things we did with the main shock is try and estimate what kind of earthquake it was, how big it was, and this table just shows all our colleagues and different partner agencies. And although the headline number is 5.7, you know, that was the very first magnitude that came out from the USGS, and it's probably a little bit high. So you do sacrifice accuracy a little bit for speed. And later, you know, we think it's probably closer to 5.5 rather than a 5.7. But we're probably not going to change the quote official authoritative magnitude because it's just too confusing to do that. But one thing is, you can see the numbers are pretty consistent in this column, even though there is some variation. And we can do other kinds of modeling of the data, and there's another way to estimate the magnitude, and looking at what we call the spectra instead of the time domain data. And if you look at the spectra, you can sort of model it, and we get about the same magnitude. And here we can tell that the duration of the main shock was about 2 seconds long, and the area of the fault that moved, that slipped during the earthquake, was about 20 square kilometers, which is really close to the area of the city of Magna. And the amount of motion that happened during the earthquake is what we call the slip, and it was about a foot, about a third of a meter. And so it's not like the whole 20 kilometers slipped all at once. What happened is you had a little slip, which is like a crack in one spot, and then over the course of 2 seconds, that motion, that crack, spread over this whole area of about 20 square kilometers. And of course, the shaking that people feel and that we all felt is much longer than 2 seconds. And that's because the energy disperses and spreads out as it travels from the what we call the hypocenter to wherever you are. And so if you take a rock and you throw it in a pond, you know, it has a very short interaction, the rock and the water, and it sinks. But then you see these big ripples that extend out and spread out. And it's sort of that kind of a thing. And so the group at Seismograph Stations, we responded just as, you know, as a high pressure response, because we were at work from home because of the pandemic, and we were still able to get out over 185 temporary seismometers, I would say within a week of the main shock. And within several days, we had many tens of extra seismometers put out. And so the green triangles are the fancier ones we put out that send the data back in real time. And then the blue are these geophone data that actually this week, some of my staff are out collecting these and bringing the data back to our data center, and then we'll look at it. So we really haven't seen much of the data from all the blue dots, but putting out those extra seismometers can really help, because it helps us do a better job of detecting and locating little tiny aftershocks. And this is our official count right now, as of yesterday. And all these earthquakes have been reviewed by our analysts. So we initially get an automatic solution, and then our experts go in and they throw away the bad data and they refine it and so forth. And so we're over 2,000 aftershocks. And on this graph on the bottom, here's the main shock, right? So here's March 18, and you just go along in time. And of course, many of us remember these two bigger aftershocks that happened. I think it was on a Tuesday night and then on a Thursday morning. And although they were a little bit bigger, they weren't unexpected. And it's only on average that the number and the magnitude decreases in time. And so there really wasn't too much unusual about these earthquakes, although it did sort of make people uneasy. And we had a lot of media requests after these events happened. But really, this is very typical behavior for a sequence of earthquakes. For a magnitude 5.7 main shock, this is a pretty typical aftershock sequence. One thing that's kind of interesting, and I'll talk about a little bit more later, is there's this major cluster here, and this is where Magna is. You can see down here. There's also this secondary cluster that's just south of the airport, and we think these were probably triggered in a sense from the stress and the shaking from down here, and there's probably a reason why there's a gap here and they're not all connected. But we are considering these to be aftershocks, as well as this big group here to the west. And one thing we're working on, there's a lot of sort of detail on this slide, but the main point I want to make is we're using sort of the more cutting edge methods right now to make what we call an enhanced catalog. So our standard catalog that I just showed is this, and with this enhanced catalog using the more sophisticated match filter and different kinds of data processing, just through April 8th, we've detected almost 4,000 earthquakes. And we just haven't finished running this enhanced technique yet. But my guess would be we're going to be north of 10,000 aftershocks when we get finished with the enhanced techniques. And we might not be able to locate all of them, but we should be able to locate maybe half, so maybe 5,000. And that's without all the geophone data. And if the geophone data are useful, we might get up above 10,000, 15,000 aftershocks. And some of the aftershocks we're able to detect are actually negative magnitudes. They're so small, their magnitude is below zero. Here's just for context, a map of northern Utah, and this big red line, this is the Wasatch Fault, and it's the longest, normal fault zone in the world. There's 10 segments to it, and there's sort of 6 central segments. And so our segment here is called the Salt Lake City segment, and the Salt Lake City segment goes from sort of maybe where the airport is, a little bit north of the airport, and then the southern boundary of it is the point of the mountain down here. And you can see there hasn't been a lot of seismic activity in our catalog historically in the central part of this Wasatch Fault zone. We know historically from our geology colleagues that there have been really big earthquakes previously, but since we've been seismic monitoring, there hasn't been a lot of action. So this 5.7 that happened is the biggest earthquake that's been recorded on the Wasatch Fault, since we've had modern instruments. It's these other ones earlier are kind of off on these subsidiary or alternative fault areas. So this was a major event. And on the right is a close-up, just showing for context. This is the Wasatch Fault here on the right going down. You can see all of our earthquakes. The things that look like beach balls, these are what we call focal mechanisms, and they just indicate what style of faulting happened. And so, what it means is that for 8 of the aftershocks, they were big enough that we could model them like we modeled the main shock. And the faulting is similar for all of them. It's this normal low angle, dipping, or normal faulting, sort of a shallow dip to the west kind of fault mechanism. And it's sort of what we expect for this region. The faulting is a little oblique, so there's a little bit of left lateral shear or left lateral strike slip component as well. So they're not pure normal. There is that little bit of oblique component. And let's see. Here's our sort of preferred model or interpretation for what we think is going on, or our model for what happened. And on the top is in map view, and you can see there's an A and an A prime here, this line. And if we slice into the map, we can look at the A prime in cross section. And all these faults, these black lines here, these have been mapped, I think, mainly by people at the UGS. And this is considered the main, Wasatch Fault zone, and this is considered the West Valley Fault system or West Valley Fault zone, this complex over here. And the yellow here and in the bottom, just that sort of indicates the valley, the sediment, whereas the gray indicates rock, hard rock. And we have an idea of what the thickness of the basin is. We don't really know the dips of these faults, but we can guess at them kind of. And so our interpretation is that you have this very steep dip here at the surface, and this would be up here at this point. And this part is called the Warm Springs fault. And we think what happens is that as it goes down, it kind of starts to kink or curve a little bit. And we think there might be an interaction here between these east dipping faults at this kink. And that's, could explain possibly why we had this secondary cluster of events here. And this is sort of predicted in a 2015 paper by, I think, Krista Ross and Mike Hilland, where they raised this possibility that a deeper earthquake on the Wasatch down here could trigger, activity on this antithetic fault system. And we've done some modeling of what we call Coulomb stress. And if you see an orange area, that's a spot where, we think, oh, there was increased stress from this earthquake. And so this area up dip is an area of increased stress. And we don't know for sure, but it's possible that these events are actually lining up on this other fault system. Here's the main sort of swarm of earthquakes that we located. You can see there might be some fine structure. There might be other little planes in here, indicating a very complicated, or if you're a geologist, maybe just a more realistic a fault zone. If you're a seismologist, you tend to just draw one big line and be done with it. And so we picked this dip here of about 30 that kind of underlines the earthquakes, and then kind of continues up and curves and meets up here at the surface. And so that's where we are in terms of the scientific interpretation or scientific model that we have right now. And as we get more data, of course, we'll continue to revise this and fine tune it. And this is my last slide. And this is just sort of, I think, especially for this group, or maybe when we're all talking to the public, these are some of the important, I think, take-home points for people to remember. And first is that this earthquake was the largest earthquake ever recorded on the Wasatch Fault. Yet, in the grand scheme of things, this was a moderate-sized earthquake. So every day, somewhere around the world, there's probably a magnitude, 5.5 or bigger earthquake somewhere. So it's really common. It's just that it happened right next to us, right? But if we did get actually a big earthquake, a magnitude 7, remember that the magnitude scales are logarithmic. So it turns out a magnitude 7 would release 90 times more energy than was released in this 5.7. Okay, so this was not a major big earthquake. And if we think about the area of the fault and the amount of stress that was released when this earthquake happened, there's still a lot of strain that is loaded on this Salt Lake City segment. So as you go south from Magna and you go towards the point of the mountain, there's still a lot of potential strain energy there. And this segment, the Salt Lake City segment, is still capable of producing a magnitude 7 earthquake. So the amount of stress relieved by the Magna event was not really big enough to change that. And this is the final bullet is just that I think, and again, this is based on work, I think, mostly from the UGS, some of the paleo-seismological stuff that's gone on with Krista Ross and now Adam Hiscock and others, is that we think there's this recurrence interval or periodicity maybe of every 1,300, 1,500 years for this segment. And we think the last large event was about 1,400 years ago. And we'll see, somebody from the UGS can correct me if that's not precise enough. And so that fits in with bullet number 2, that there's still a lot of strain and, there's still a lot of energy waiting there on the fault that can be released. And so people shouldn't really let down their guard. We shouldn't scare people and say the risk is way higher. It's about the same, but we still have this major hazard here in the Salt Lake City region and really along the Wasatch Fault. And so maybe I'll stop there. Yeah, so generally the bigger the earthquake, you know, the longer the source, and the longer the source duration, the longer the shaking is going to be. And so when you have these giant earthquakes, you know, like magnitude 9s, the rupture can go on and on for minutes, you know, and that's just the rupture. So, you know, the shaking could be longer in the future for a bigger earthquake. And the duration depends a lot on resonance. So if you're in a building or an area, you know, with sediment, sometimes it's like you can get ringing, and so it's like if you flick a wine glass, you know, that you flick it and then it'll just keep ringing and ringing and ringing because if you've excited it at one of its modes or whatever. And so anyway, the shaking can, I think we do have some records. I haven't looked at them, but where the shaking on one of these accelerometers in the valley goes on for like a minute, and it's because of where it was positioned. And that's the kind of thing, of course, that's very interesting from an engineering perspective, is looking at how these things varied based on the site and how the duration varied. And the other thing is, with a bigger earthquake, the actual magnitude, not just the duration, but the G-force of the shaking is going to be stronger as well. So it's really going to be terrible if we get, you know, if we have the 7 on the Salt Lake City segment. So as far as I'm aware, I've seen 5 different solutions for the main shock, and 4 of them have a west dip between 30 and 35, or let's say 30 and 36. And the one outlier is the USGS W phase, and that's the one that you're referring to that has the steeper western dip. And I do consider it to be an outlier. So by the way, the USGS has another moment tensor solution, right? That's what they call their MWR, and that one does agree with ours. It's only one of the 2 USGS solutions that's an outlier. And my sort of, what I think is going on is that's their W phase solution, where they're pushing that as fast as they can to get that out because they want that for the moment magnitude. And I just don't think, you know, it only uses these really long period body waves. It doesn't use the surface waves because it doesn't wait that long for the surface waves to come in. And I think in general, you see some really big non-double couple components that are unphysical, I think, sometimes on those W phase solutions. And I've talked to Gavin about it, and Gavin, I think, would admit, and Harley and those guys, you know, that that they don't try and interpret the mechanism too much from their W phase solution. They're more interested in getting the W phase solution so they can get their MWW, which is their preferred early moment. But as you can see, sometimes that's not going to end up being the best moment either. So there's always this trade-off between speed and maybe accuracy. And they know this. I don't think they would disagree, you know, with these things. And sometimes it is important to get something out really quick, even if it's not the most accurate solution.